Hi guys, I got some post from my PCB manufacturer, and what's inside? We have two packs of PCBs. One PCB, I already mentioned it in the previous video, is the new version 4 controller, and the other PCB is an extra board we need for one of the features of the controller. So let me just tell you what we have new on the version 4. So there is first some integrations of what I have just previously added by temporary pins, like the column meter, etc. So this is now all integrated on the PCB now directly. And then, you know, I had a 12 volt issue when I was in Austria, and so this board will also monitor the 12 volt bus by itself and show on the app if it's present or not. And then we have two main features. One already kind of slipped away into standby, because initially I thought I was kind of tending to add the third charger, not to be a fixed output charger, that it should be a variable output charger. I saw one in AliExpress, somebody selling something like this, and that charger would have a manual potentiometer on it, and you could have set a current between 2 and 25 amps, or there's also a smaller version of that by hand there. And so I thought, that's kind of a good idea. We could actually let the controller set the potentiometer. But to do something like this, you need something called like a digital potentiometer. So this is a small breakout board of a digital potentiometer. So this would replace the manual, and a digital device like a microcontroller could then digitally, like magically, set a value on that potentiometer. But I then still decided to go with a fixed output charger, just because, you know, I would have to order that other charger. I don't know what kind of value of manual potentiometer there is inside. You know, it could have also kind of failed, that idea. So it was a little bit too risky, and I just went with the fixed output charger. Nevertheless, with more research or something like this, it could still be done one day. If I wouldn't have to add another charger, I could then just go with the variable output charger then. And then the main feature still, the new controller will be the addition of a cell voltage monitor on the battery pack. So that is the second PCB. It is here, of course, a breakout board, which is somewhere extra, similar to a BMS board at the pack, and then there's a cabling and a connector at the controller, where this will then be plugged in. We will talk about the cell voltage monitor in a bit. You have already seen me soldering stuff, so I'm now just going to prepare those boards, and then I will show you the board, how it looks like, and what we are going to do with it. Yeah, finished soldering the boards, cell monitor and controller board version 4. But here at the cell monitor already stopped working on it because there's a problem. Do you see these pins here? I had to put almost diagonal. The reason, I have used a footprint from somebody in EasyEDA when I have designed the board from this multiplexer breakout board. But this seemed to have to be an older footprint, and these boards, the breakout boards, they got smaller. And now this row of pins here. This header should have moved by about 2.5 millimeters, this one unit. Yeah, I put another header here, so this will be just a testing board. And yeah, we are going to test and just show that the concept is working. Yeah, but otherwise you see the row of SMD resistors. These are the voltage dividers. Yeah, I can use it, you see, I can put it on here, but I of course don't like when something is not correct. So what I've done, I have already redesigned the board. The file is out for manufacturing. I will get a new one and then everything will be perfect, how I like it. The version 4 controller. I have brought here the version 1 controller with me, so that you can see some differences. Yeah, you see this version now is already packed full with new connectors, and I also started to use SMD components where I can. The controller will be then built into the Powerwall after I have all the software, the code rewritten for it, and then everything will go into the Powerwall. Let's talk about the cell monitor quickly. So cell monitor, as you know, for the time, the only thing my controller is doing is measuring the total pack voltage. For the cell voltages, you know, I'm occasionally taking my multimeter, then I'm going out to the pack, take some measurements, yeah, and then I decide if there's some necessity for balancing or whatever. It's just more or less for interest, because the pack like this, you know, it's not too much going on inside a pack. But still, if this feature is automated somehow, it can save a lot of time and work, of course, because going to each cell and measure by hand, it takes some time. It's probably kind of boring. And this can of course be done within a moment of time by the controller and just displayed on the screen. And of course we have two possibilities. Just use it primarily as a monitoring feature, so you just have the voltages presented, but also of course the controller can then take some actions if some cells are showing out of limit, for example. This is very, very unlikely at my setup, because I am absolutely not going into any area of a limit at my cell voltage levels. But you know, you never know. The devil is in the detail. If there is a cell running out of control by whatever reason, which is again very unlikely with lithium iron phosphate, then of course, if a high voltage level or a low voltage level is reached, the controller could also then decide to stop any charging, discharging or whatever. What is the challenge now? The challenge is, of course, we have a lot of measurement points. We have 16 cell strings, so we need at least 16 points of measurements, which the controller again has to deliver. So there is hardly any microcontroller which has so many pins. I'm using already the Arduino Mega. It has 16 analog pins where you could do this kind of readouts. Those pins are actually not precise enough for the job what we need to do. We only have a 10-bit analog to digital converter on the Arduino, but in our case, as we cannot take measurements always at cells directly between the plus and minus, we have to deal with a much higher voltage range. So we are actually taking measurements between ground and each plus of the battery cell. So it will be a voltage somewhere between the first nominal voltage 3.2 until the 16th cell, which is nominal somewhere about 50 volts, right? So this cannot be directly measured by the microcontroller or by any analog to digital pin, and that's why we need a specialized board which is breaking down all those voltage points to a usable level. And this is what our voltage monitor board is actually doing. So if you look at this, we have a board here with, here on this side, 16 inputs, or 17 if you're exact, because we have ground, and then 16 voltage values from each cell string. And then you have a row of resistors here and here, and this is nothing else than voltage dividers, which are breaking down those high voltages, much too high voltages, in some cases down to 5 volt maximum, which then our analog to digital converter can read, right? But how do we access those extra pins here? For this I have chosen a multiplexer. This is this board here. It's a finished breakout board you can buy, and this is 74HC4067 multiplexer. It is a 16 channel multiplexer, and this can switch through one of the 16 channels to one measurement point, and from there we can then take our measurement. Right, so it's quite very simple. You can imagine this as a corridor with 16 doors. We can go to one door at a time, open it and look inside, take a measurement in our case, then close the door, go to the next one and repeat the action. Yeah, so very simple, very cheap in this case also, and it will be just another task for our controller, which it will do with every loop, just adding one more task to its loop. That is all about the cell voltage monitor, and here we are going to test this first, of course. That's why we are going to take this failed board. The revision of this is already under manufacturing and will be then maybe here now in about 2 weeks, and then all this will fit perfectly. But I will use this board now as a demonstration test board, and I will then set this up here with my Arduino Nano on my breadboard, and we will test this and do measurements on the Powerwall, just with a few pins, not all 17, not all 16 channels. It's just about writing the correct code, demonstrating that it works, the idea, and then when the new version comes, I will just make one final one and then also install the controller. So in case you're interested about the sketch, just a few words to it. I'm using the library from Patrick Wasp. It's very, very simple. It's only one command you need. The library here, I have defined a few variables. So for the channel voltage, these are all arrays. I have 16 variables in each array. Then the string voltage, and then the integer read from our analog to digital converter. But this is defined here as a command, so you see the channels, the digital pins are defined. So 4 bits which are telling the multiplexer which channel you are talking with. But this command is then defined like that you only have to enter the channel number and this will be set automatically. It's very nice. Okay, so in the setup This is all preset, and then in the loop, in this case we are just reading the integer value here directly from our analog pin of the nano. Then we are calculating an initial voltage, so this is a value somewhere between 0 and 5 volts, right? And this represents 5 volts would represent 1024 as an integer value. But of course this is not telling us anything, that's why we need to correct it. And the correction is basically just calculating what is really there on our voltage divider. So if you look into these formulas here, in the part here in the back, this is our voltage divider here. So we are taking our voltage which we just read, and this will be then corrected by the voltage dividers. In this case, for the fourth cell, there we have a 30 kilo ohm upper stage resistor and a 10 kilo ohm lower stage resistor. So they are added together, 40 kilo ohms divided by the lower stage resistor. And then the result of that calculation is then already the real voltage at that cell, right? Which will be somewhere around 13, 14 volts, right? And then at the end, I have a correction value because, you know, resistors, they come with tolerances, etc. This can then be at the end corrected by comparing the reading to the multimeter. So this is then here already done for all 16 cells. If you then continue here looking, so these voltages are then presented, and after the last voltage is taken, we're going to calculate the individual string voltages. So how is that done? Very simple. The string voltage is always the voltage taken at that cell minus the voltage present on the previous cell. So if it is again our fourth cell, this would be the voltage on the plus pole of the fourth cell minus the voltage of the plus pole of the third cell, and that is then already the string voltage. And this I'm then presenting here on the screen, or later on this will be then presented on the display of the controller. If you would do this extremely quickly without having any delay between switching and measuring, then your measurement would be not correct, because the voltages first need to settle a little bit on the measurement pin before you can take the measurement and then switch to the next channel. So you always need a delay. That's why I'm not making all these measurements right after each other also then in the controller, because that would take quite some time, maybe up to 2 seconds, right? Because you always have to allow some delay between measurements. So I will just do always one measurement every loop. When it comes to the controller, then switch the channel, and until the controller comes to its next pass on the loop, so there will be at least a second passing, so the voltage can settle without problems. And that's already it. We are going now to the Powerwall and doing some testing, and if the test is successful, I can then add this code to the code of the Powerwall. Okay, I've built my test setup here at the Powerwall. I have connected my harness here, but only for the first 3 strings. That's well enough for the test as we need it. But still here also, before you connect anything of your high voltage Powerwall or battery system, before you put your connector into your BMS or whatever electronics, if all the connections are correct. The reason is your battery system has much higher voltages than most of electronics can deal with if that electronics is not built for high voltages, which is usually not done. So here on our Nano, we can, on our measurement setup, we can only accept voltages up to 5 volts, and the Powerwall will deliver much more than that. So that's why these voltage dividers are built in here, and before we connect we check every step here. Okay, that's correct. And I'm going to plug in this now into my multiplexer board, and then we are going to read out the voltages there. So no magic smoke on the Nano, which is good. And let's just run this. Okay, and we can open our serial monitor. Yeah, and as you can see we have readouts. Let's stop this so that it does not auto scroll. For example, here 3.39 for the first measurement, then 6.78 second measurement, next 10.27, and then string voltage is calculated 3.39, 3.39, 3.49. So these voltages are too high. They will have to be corrected comparing with the multimeter. And you also can notice that the third readout is already kind of very high. But this is because, you know, at every cell step higher, the precision is getting lower, right? So in this case, the 10-bit ADC, we only have 1024 values to represent the first direct voltage readout measurement, and then at the second we only have half of the precision left, and then on the third already only 1/3 of it, and so it's only like 300 values which can represent the third measurement in this case. So that's why we need a much higher precision ADC, and the 16-bit ADC which is used at the Powerwall controller is already 65 times more precise than this 10-bit ADC which is on the Nano. So that's why on the Powerwall controller, even on the last cell measurement, we will be 4 times more precise as we are here on the first cell readout. So there, no problem. But as I said, so these ones here, the measurements need to be corrected now by using the multimeter as reference. These have to be then put into the code, and then this will be similar to a multimeter readout. Okay, everything is working perfectly, and we can transfer the code into the Powerwall controller. Just waiting for the new board, final board, and then everything will be installed into the Powerwall. We have tested now our cell voltage monitor using a multiplexer at the Powerwall. Everything works so far. In the next video we are going to install the controller and do some final installations or changes, and then everything should be done. Okay, so that should be enough for today's video. Thank you very much for watching, and please comment again, subscribe to the channel, like the video. Thank you. I see you next time.